Okay, in this segment, we're going to talk about some of the rules of integration. These are like the rules of differentiation we learned. In your calculus class, you'll go through the direct details on how to get to all of these things. This, once again, is the quick and dirty version. You may not use this as an excuse in your calculus class to explain that you already know this stuff. This is just a practical guide to taking integrals. So let's take, for example, if I have the function f of x equals x squared. We know that by the power rule, f prime of x is equal to 2x to the first power, right? We've effectively, or just 2x. We've used the power rule for differentiation and reduced the power by 1 and brought the power down in front. So the derivative of x to the n is n x to the n minus 1. Well, we're going to look for the integral version of basically the reverse of that. If I were to take the integral of x to the n dx, the answer is x to the n plus 1 over n plus 1. You can see, if you're sharp, that this is the reverse of the derivative. For example, if I took the derivative of x to the n plus 1 over n plus 1, I would get x to the n, right? Because the derivative of x to the n plus 1 over n plus 1 is equal to n plus 1 times x to the n plus 1 minus 1 all over n plus 1 from the original statement. You'll notice that these cancel out and I'm left with x to the n. So you can see how the derivative and the integral are inverse functions of each other. They undo each other. So if I took the derivative or the integral, I should move back and forth. One trick that has to be clear here on what is effectively the power rule for integration is that we have to worry about whether or not we've lost an important constant somewhere along the way. So that's what I'll show you next. Okay, so let's figure out what happens to a constant that might have been in the equation originally. So if instead of f of x equals x squared, we had f of x equal to x squared plus 3. If we differentiate this, take our first derivative, using the power rule, we get an answer of 2x. Perfectly fine. Derivative of a constant is 0, so we would not represent that. Now, if we were to integrate this thing back and get the integral of 2x dx, using the power rule for the integral, we would raise the power by 1. First, we would raise the power, so we'd have the 2, raise the power by 1, so that would be x to the 1 plus 1, or 2, and divide by the new power, which was 2. And so this would end up being x squared. And you'll notice that we did in fact get back part of the function, but we lost the information about the constant. This is an effect of the what we call a indefinite integral, meaning that there's a wide variety of functions whose derivative would all be the same. So we are no longer selecting a specific answer back. So what we need to do is we need to put the plus c on here to recognize that there's an infinite number of functions that we could take the derivative of to get 2x. And those are all functions that have an x squared term plus a constant. You did need to use some additional information, usually known as initial conditions, to determine what the constant is. So if we knew the value of the function at one point, just at one value of x, we could use that information to determine our undetermined constant c. So it's just something that we're going to remember, that when we take integrals, we need to throw that plus c in there a lot of times. You'll learn a lot about this in your calculus class. Okay, so let's go ahead and do a couple more examples of the power rule. Let's say that I wanted to do the integral of 3x to the fourth dx. One of the rules that we're allowed to do is any sort of constant that is multiplied by our function, we're allowed to bring that constant out in front. So we normally, while taking integrals, would rewrite this as 3 times x, the integral of x to the fourth dx. Now I can apply the power rule to this particular term, and I would get 3 times, now I'm going to put in the answer of my integral. Remember, the power rule for integrals are raise the power by 1, so it's x to the fifth, and divide by the new power. And since this is an indefinite integral, I have to put in a plus c. So my answer would be 3/5 x to the fifth plus c. Let's do another one. Integral of 1 over x squared dx. Now here, you may look and say, well, oh, wait, that's not the power rule. But it is. It's there. It just is in a slightly different form. So you have to do some rearranging. So when you have things in the denominator, usually you want to take a moment and rewrite them in the numerator using a negative exponent. So I can rewrite this, and you can see that these two things are exactly mathematically equivalent to each other. I can now use the power rule, and I can raise the power by 1. So minus 2 plus 1. Make sure that you remember that you're adding a positive value to a negative number. And then I have to divide by the new power. So minus 2 plus 1 is minus 1. So I would end up with x to the minus 1 over minus 1. And then simplifying this would be negative 1 over x plus the constant. So there's some examples of power rule. Now here's a tricky one that you need to keep track of. The integral of 1 over x dx. You might think, using what I just did above, that this would become integral of x to the minus 1 dx. Using the power rule, I would get x to the minus 1 plus 1 all over that same minus 1 plus 1, which would be x to the 0, which is okay, divided by 0, which is not okay. This is a problem. Turns out that the power rule does not apply to this integral. It becomes a very special integral that you'll learn all about later. One of these ones where you may just have to memorize it. The integral of 1 over x dx is equal to the natural logarithm of x. Something to remember. Okay, now let's move on to a function that is a polynomial. Turns out that the power rule still is going to apply. So if I had something like 3x squared plus 2x plus 3 dx, the operation of taking an integral is distributive. So I can rewrite this as 3x squared dx plus 2x dx plus integral of 3 dx. And I can do each of those three integrals independently of each other. Once again, I can rewrite this as 3 times the integral of x squared dx plus 2 times the integral of x dx plus 3 times the integral of dx. Multiplicative constants are allowed to come out front. Now I use the power rule. 3 times x to the third over 3. I raised the power by 1, 2 went to 3, and I divide by whatever my new exponent is. Plus 2x squared over 2 plus, okay, now the trick is, what do I do here? You can think of this as two ways. You can either think of this as the integral of x to the 0 dx. I can raise the power by 1, so I would get 3 times x to the first all over 1. Or I can just remember that the integral is the inverse of the derivative. So the integral of a derivative is just the variable itself. So the integral of dx is just x plus a constant. So if I simplify this out, I get x cubed plus x squared plus 3x plus c. That would be my original function. If I take the derivative of that, you'll notice that it gives me this. So the process of integration is distributive. So we've covered the power rule for integrals. This is the simplest of the integral rules, and turns out that there are several other integral rules that will usually get you back to power rule or some other definition like integral of 1 over x where you know the answer. We'll cover that in another section.